we are going to apply a differential mode signal, VIDN, to the gate of transistor M1. We are going to apply a differential mode signal, -1/2 VIDM, to the gate of transistor M2. We're going to load that differential pair with our CMOS current mirror. Some voltage VDD here. Let's see, this is M2. This guy will be M3. This guy will be M4. And for now, we're going to bias this guy with some current I reference. Okay. And our goal here is to figure out what our output differential mode small signal will be. So effectively, we're getting into the nitty-gritty of how this thing works as an amplifier. So I'm going to draw the small signal equivalent circuit for this guy, and it's going to be messy, but that'll be okay. So I'm going to start with the PMOS side. And so these two guys right here represent transistor M3. And we will no longer be neglecting channel length modulation. So we will have some resistance R out 3 in parallel with a dependent current source that gives us GM3 VSG3 amount of current. So up here is where our power supply voltage is, VDD, which looks like an AC ground, making this node S3 and this node the drain of 3. And then over here will be our gate terminal. This will be for transistor 3 and 4, which means that this voltage is VSG3 and this voltage will be VSG4, and the gates of transistors 3 and 4 are tied together, which is why I've drawn them that way. Over here we are going to have transistor M4. We'll have GM4 VSG4 in parallel with our out 4. That transistor is tied to VDD, so this guy is S4. This guy is D4, and our PMOSs are pretty well defined here. The drain of transistor M3 is tied to the drain of transistor M1. So we'll have GM1, VGS1, and R out 1 respectively. Over here, this is our gate for transistor 1. This is our drain for transistor 1. This is our source for transistor 1. So at the gate of transistor 1, we apply that signal 1/2 VIDM. This is our gate source voltage, VGS1. Similarly, over here on the right, the drain of transistor 4 is tied to the drain of transistor 2. current source is GM2, VGS2. And so this is the drain of 2, source of 2, the gate, that's not a lowercase g, 2, and then here we have our signal -1/2 VIDM. So this guy is VGS2. Our sources are tied together. I'm going to call this node here in the middle voltage Vx. And before we do anything else, I want us to take a look at this guy, okay? So I'm going to draw this bit here in red. Fully understanding that I'm about to erase what I'm drawing here. So, all right. So when we biased our differential pair, or when we loaded our differential pair with PMOS current sources, this is what our small signal model would have looked like, okay? Everything is perfectly in balance, okay? The left-hand side exactly matches the right-hand side. Everything is purely symmetrical. And so that's how we knew that that voltage Vx was equal to 0. Or it's not how we knew that voltage Vx was equal to 0, but as a consequence of that symmetry, that voltage Vx was equal to 0, okay? For this system, the change that we have is this. So I would argue that while the circuit isn't perfectly symmetrical, it's pretty darn close because we've just tied that gate to a node. It's the only difference there, right? So Vx isn't going to be exactly 0. It's just going to be close to 0 because we're close to symmetrical, all right? So let's call this node down here ground. It's not going to be quite ground, but it's going to be close enough for what we're doing, all right? I'm going to call the nodal voltage here Vy because it will be critical. And then we take our output here. So this is our differential mode output voltage, VODM. So anything about this before we get into the analysis not make sense? Let's start there. All righty. So since we have some, or with the assumption that Vx is equal to 0, we can obviously see that VGS1 is exactly equal to 1/2 VIDM, right? Which means this current source is going to be carrying a current I1. And down here, we can just simply say that I1 will be exactly GM1 multiplied by 1/2 VIDM. On the right-hand side, we can easily see that VGS2 is -1/2 VIDM, which means that this guy is carrying a current down of -GM2 1/2 VIDM, or a current up I2 is equal to GM2 times 1/2 VIDM. Is everybody okay with that? So literally saying because it's got a negative sign, it's flowing in the opposite direction. Circuits 1, level stuff. All right. Now, this bit is hopefully a review for what you guys covered in, I think we probably talked about this in 336, but let's look at this current source here. Okay. This current source has a current of what flowing through it? GM3 times VSG3, whatever that happens to be, right? It has a voltage drop of VSG3 over it. So since the voltage and the current are linearly related, that guy is actually just behaving as a resistor, having a value of 1 over GM3. So I'm calling this guy RM3 is equal to VSG3 divided by GM3 VSG3, or 1 over GM3. That looks too much like GM cubed for me. Okay. So why that's important is because if we look here between node Y and ground, we have this current source GM1, BGS1. We have this resistor R out 1, that resistor R out 3, and the resistance of that current source 1 over GM3, all connected in parallel. So VY, which is the voltage difference between this node and ground, is simply that current flowing through those 3 resistors connected in parallel. Does that make sense? Okay. So we can say that VY will be negative GM1 times VGS1, which is 1/2 VIDM, multiplied by R out 1 in parallel with R out 3 in parallel with 1 over GM3. Since 1 over GM3 is typically much, much smaller than our output resistances R out 1 and R out 3, this will look like approximately negative GM1 divided by GM3 multiplied by a factor of negative 1/2 VIDM. So we are making an assumption here that 1 over GM3 is small enough to be the dominant factor in this parallel combination of resistances. Okay. So why our determination of VY is so important is because VY is exactly equal and opposite to VSG3 and VSG4, right? We know that these two guys are identical, and this is also equal now to negative VY. So that voltage VY establishes the current that is being sourced or that flows through transistor M4. So we can say that the current flowing here, I4, is GM4 times negative VY, which is going to be negative GM4 multiplied by negative GM1 over GM3 multiplied by 1/2 VIDM. And obviously, This negative sign cancels that negative sign. And if transistors M3 and M4 are matched, which they should be for a current mirror, that means GM3 and GM4 are the same thing. So this guy in the numerator cancels this guy in the denominator, leaving us with a current of positive GM1 times 1/2 VIDM. So if we apply, scroll up here real quick, Kirchhoff at our output node, we can see that a current of I2 and I4 are flowing in, and a current of VODM divided by R out 4 plus a current of VODM divided by R out 2 are flowing out. So effectively, using Ohm's law, we could see that VODM is simply I2 plus I4 multiplied by R out 2 in parallel with R out 4. Oops, that went slightly too far. Substituting in our relationships for I2 and I4, this is going to give us GM2 times 1/2 VIDM plus GM1 times 1/2 VIDM multiplied by R out 2 in parallel with R out 4. And since transistors M1 and M2 should be matched, GM1 and GM2 are equal. And so we can say that this is simply GM2 multiplied by R out 2 in parallel with R out 4 multiplied by 1 whole VIDM, giving us a voltage gain. AV is VODM divided by VIDM of positive GM2 R out 4, or R out 2 in parallel with R out 4. Sorry, the order of the resistors don't matter here, but I'm just trying to be consistent. So we see that we get the exact same amount of gain that we had for our current source loaded differential pair with a current mirror loaded differential pair, but now we have a single-ended output. So we get literally just as much gain as we got before, but it's all being sent to a single output terminal as opposed to being distributed between two output terminals. We no longer have an inverting amplifier because a positive VIDM gives us a positive output. So all kinds of good things have happened. So we have a formal description of what the hell is going on that matches pretty well what our qualitative description was last Monday. All right, so how do we maximize the gain of this circuit? What design choices do we make, right? So I'm going to write down our voltage gain equation again here real quick. We know that AV in this case is GM2 times R out 2 in parallel with R out 4. As a refresher, our transconductance GM is the square root of 2 mu Cox W over L times ID. Out is 1 over gamma ID or capital lambda ID. And because we want all of our transistors operating in the saturation mode, ID would be 1/2 mu Cox W over L times VGS minus VTH squared. Forgot to write squared on my notes, right? So we don't have control. Obviously here, the bigger we can make GM2, the better, because we get more gain, right? That's pretty fair. So we need to figure out how to make transistor M1 and transistor M2 have the maximum value for GM2. So obviously, as our drain current goes up, GM goes up. So our ability to control that. But what happens to R out as our drain current goes up? Does it get bigger or smaller? Smaller, right? And since our gain also depends on the output resistance, messing with ID too much can wind up biting us in the butt. But we can see that our transconductance depends on our width over length ratio, and ID does as well. So that's where we can do most of our tinkering with maximizing this guy, right? So we have to choose W over L 1, 2 such that GM 1, 2, right, and R out 1, 2 are as large as, and then separately, for the same reasons, we have to make sure that our aspect ratio for transistors M3 and M4 give us a maximized value for R out 3 and 4. Make sense? All right, so with that in mind, so this is how these guys are going to behave for the small signal. Now let's mess around and finally get rid of these ideal current sources, okay? So we can update our design slightly. Call this guy BN1 for transistor M1, M3. So most of this is going to be identical to what we've been doing. Sorry, that's the wrong type of transistor. Or So this is going to be M5, and I'm going to call this voltage here V bias 5. And this will be single-ended output V out. So if we want to make this circuit behave effectively identically or as close to identically as possible to our previous circuit, what are the constraints that we have control over to make this happen? So we will have to choose V bias 5 and W over L5 such that ID5 is as close to our reference current that we designed this guy for as possible, while having R out 5 as large as possible. Let's talk about this constraint of having R out 5 as large as possible. So the obvious reason why we want to have R out 5 as large as possible is because we're trying to approximate an ideal current source, which has an infinitely large internal resistance. A slightly less obvious reason, but I believe I've talked about it in this class previously, is that having R out 5 be as large as possible, let's scroll up here. Right? So we are going to have a very fixed ID in this case, right? Because ID for transistor M5 is effectively that I reference current that we wanted to have. So we can't monkey around with that or we're going to mess, it's going to have large scale effects, right? So that means we need uppercase lambda to be what? As large as possible or as small as possible? As small as possible, right? So how do we make that value be as small as possible? We don't have any control over lambda per se, but we have a control over its effects, right? Because that's our channel length modulation coefficient. It is a measure of the change in the channel length, or the relative change in the channel length with respect to the actual channel length, right? So if we make our channel significantly longer, gamma represents a smaller change. So effectively, we maximize R out by making that current source transistor effectively as large as we can make it for our given footprint, which has the added benefit of making that current, that DC bias current ID5 as stable as possible, because we're making it less subject to channel length modulation shifts as well. So it is literally a fantastic move here that we have this dependency. It's easily solved. We just make the transistor have a very large channel. Or I think as we talked about it earlier, we could also cascode it and that would have a similar effect. All right, so these conditions are pretty easy to accomplish. We just establish our bias voltage such that the VGS we get winds up giving us a current, an output current of I reference, or as close to I reference as we can make it. And we use the largest length that we can physically accommodate to keep that current level stable, which happens to also maximize our output resistance there, making that tail transistor M5 look as close as possible to an ideal current source as we can make it with a single transistor, okay? Now, One problem that arises from using an actual transistor to do this instead of an idealized version is that if we're not careful about what our common mode input voltages are, we can accidentally push transistors out of the saturation region much more easily, right? So before, and I think I demonstrated this in 336 to my class, with an ideal current source, we can put very low common mode voltages at the input, and we'll just drive that node to negative values. And the ideal current source can handle that because it's an ideal current source. But we can't push, let's call it node X here, too low. So we're going to look at node X, what's going on with it, because that's going to be important. Let's call this guy here, again, node Y, and our output, I think it matters, but I'll call it node Z for the hell of it. All right. So for our large signal analysis here, we are going to specify an input voltage. All right. So let's say that we have VN1 is equal to some quantity VICM is also a DC common mode signal, and these guys will wind up generating an output common mode signal. Okay, so effectively, we're going to see that our output signal has a DC operating point associated with it as well, which is a consequence of having a single-ended output here. Okay, so since VN1 and VN2 both have the same DC voltage level associated with them, it only makes sense that, actually, hold on, let me draw this here. So I didn't define ID5, so let's do that real quick. That's just the current being sourced by or passing through transistor 5. So we're going to have some quantity VGS1 here. We're going to have some quantity VGS2 here. And because VGS1 and VGS2 are equal, we'll have identical currents, which will be exactly 1/2 ID5. Everything okay with that? All right. So from that relationship, we can say that our voltage at node X, which is the drain voltage for transistor M5, is VICM, our common mode input voltage, minus our DC gate source voltage, VGS1, 2, and that voltage depends on that current ID5 that's flowing through it, right? So if we were to decrease our common mode voltage, then obviously Vx decreases as well, up to a point where Vx is so low that it is exactly, the gate voltage is exactly one threshold voltage above that quantity Vx, right? Which is where the edge of saturation occurs. If we go beyond that point, we push transistor M5 out of the saturation region. And what's interesting because of effectively the size of this guy and the fact that it's going to, the size of it and its stability, because it's going to be really kind of pinned at our saturation mode level, even a small dip there will cause a very abrupt shift in our reference current for our whole system, meaning that if, as soon as we push it out of saturation, the amplifier is no longer an amplifier. It's hot garbage, okay? So we can establish what is a minimum input common mode voltage. VICM minimum. And that will simply be VD sat 5 when it carries a current of ID5 plus VGS12, where this value is calculated when transistors M1 and M2 are carrying a current of 1/2 ID5. Any common mode voltage below this kills our amplifier. Make sense? All right. So what happens if we were to increase the common mode voltage? All right. So what current is being carried by transistor M3? So recall that M3 and M4 form a current mirror, right? A PMOS current mirror, where transistor M1 is generating the reference current for that mirror. So if M1 is carrying a current of 1/2 ID5, M3 is supposed to be carrying a current of 1/2 ID5 as well. If M3 is carrying a current of 1/2 ID5, which is a constant value, depending on what bias voltage we apply there, then we could say that this voltage, VSG 3/4, is constant. Does that make sense? If the current's constant, then the voltage present at the gate has to be constant as well. And so we could say that this voltage VY is going to be exactly VDD minus VSG 3/4. Using Kirchhoff's voltage law, right? So that voltage VY is pinned at that value. As long as V bias doesn't fluctuate, VY, or as long as V bias doesn't fluctuate and VDD doesn't fluctuate, that value of VY is pinned there. Well, that's the drain voltage for transistor M1. It can't move. If we increased the common mode voltage at the input of M1, we would see that Vx also increases, which is really just going to drive transistor M5 further into saturation. So it's no longer going to be the problem, right? So effectively, this VGS1 term, VGS1, the difference between VGS1 and Vx is going to be pinned at VICM. As that gets larger and larger and larger, that potential difference is getting larger and larger and larger. We run up to a point where we're going to push M1 into the triode region because VY can't move to accommodate the change in the input common mode voltage, right? So we'll find that VICM max will occur when our gate voltage is exactly 1 VTH above our drain voltage, which corresponds to a value of VDD minus VSG 34, which is evaluated when transistor 3 is carrying a current of exactly 1/2 ID5 plus, right? So that's VY itself. We can't have it go beyond one threshold voltage past that, or we push it out of saturation. So we have an input common mode voltage minimum and an input common mode voltage maximum. These two things together form what's called the input common mode range, or ICMR, of our op amp. This is literally something that you can look up on its data sheet. So we can actually see similar effects if we allow our output voltage, our DC component of our output voltage, to change by too much, right? So on the left-hand side, VY is pinned. That the node between the drain of transistor M3 and the drain of transistor 1 is at a fixed voltage, right? So M3 will never go outside of saturation unless the amplifier doesn't work correctly. There's no way to push it out without messing with V bias 5. On the opposite side, though, that node VZ floats, depending on what we put into our system, right? If we push it too high, it'll push transistor M4 into the triode region. If we push it too low, it'll push transistor M2 into the triode region. So there's a certain amount of output, DC output voltages that we can get here to keep our amplifier operating correctly. And we can define them pretty easily, right? So as the output common mode voltage increases, this will push M4 into the triode region. And so we would have VOCM max would be equal to VDD minus VSD sat for transistor M4, evaluated at a current of exactly 1/2 ID5. And as our output common mode voltage decreases, we'll see that there's a minimum level VOCM min, which is equal to VICM minus VTH2, right? So effectively, that means that our drain voltage for transistor M2 would be within a VTH of our common mode level, which is the input to the gate source voltage for transistor M2, causing it to fall out of saturation, and therefore we have an output common mode. That is not how you draw an M. Range OCMR as well. This is another thing that's literally on the data sheet for an op amp. All right, so that's all that I have prepared for today. And we have a decision to make because we effectively only have 2 class meetings left as to what we want to talk about. So there are two topics that we could address. One is we could address effectively what happens when you cascode literally every part of this guy, forming what's called a telescopic op amp. So effectively you get a really high gain, but you're crunching your input common mode range and your output common mode range on the DC side to get a very, very large low frequency gain for small signals. So we could talk about that. Or we could revisit the frequency response of these guys and talk about compensation, which is how you connect the second stage to make one of these actually able to drive something other than a capacitor. So which option do you want to talk about? So I got 1 vote for number 1, telescopic. 2 votes for number 2. 3 votes for number 2. Another vote for, okay, so there's only like 9 people in the class and only Sergio voted for number 1. So we're going to talk about the frequency domain stuff. It'll be okay, I promise. All right. So that's it for me for today. I will see you guys on Friday.